We're on the module pricing and valuation of interest rate and other swaps. Our first LOS describe how swap contracts are similar to but different from a series of forward contracts. What I'm going to do is a little review of the implied forward rates, and we will slowly lead in to contrasting a multi-period contract where one side is a swap, the other side is a series of FRA contracts, to see how they are the same thing. It's just a swap. Simplifies the whole thing by saying instead of having a whole bunch of forward contracts, let's just have one that has multiple exchanges of cash flows. And in doing that, we're going to need a rate, one fixed rate, that is sort of a combination of all of those other contract rates, all of those other multiple fixed rates in each contract. So let's start with just a brief review, and I will painlessly lead you in to the swap. Let's take a three-period timeline here, and we have three spot rates. Our first spot rate for the first year is 1%, a 2-year spot rate is 2%, and a 3-year spot rate is 3%. And a spot rate is for a single cash flow at a single point in time. So a 1-year spot rate is just for a cash flow at the end of 1 year. A 2-year spot rate, recall, is for a single cash flow at the end of 2 years. If we have these three spot rates, we can calculate what the implied forward rate is between these two periods of time and these two periods of time. The implied forward rate for the 1 year period, 1 year out, is 3.01%. We've seen this. And the implied forward rate for 1 period, 2 periods out, is 5.03%. And just to see that we would be indifferent here, 1.02, if we have a single cash flow at this point in time, the spot rate is 2%. 1.02 squared is the same as 1.01 multiplied by 1.0301. We get the same thing. And for the 3-year rate, we can see the same thing. We can use the 1 period forward rates, 1.01 times 1.0301 times 1.0503, and it would be the same as 1.03 to the power of 3. They're the same thing. Now let's say that in terms of the FRA versus the swap here. So what we can do is we can deposit. If we're making a deposit, we'll make a deposit up here, we'll borrow down here. Let's say we make a deposit for 1 year at 1%, and we can short the FRA at this point in time. We're going to make a deposit for 1 period, and we'll short the FRA at 3.01. That means if the rate drops, we're locking in 301. If the rate drops, the FRA pays off, so that we're guaranteed the 3.01 for our next period deposit. Well, we've already shown that if you get 1.01 plus 3.01, it's the same as getting the full 2%. You're just locking in the rate. Or you can, as I say here, or you can deposit at 2% for 2 years. Let's say we're borrowing. You can borrow at 1% for 1 year, and we can go long the FRA. Again, at this point in time, we'll lock in 3.01 because we don't want rates going up. If rates are going to go up, we go long an FRA, and it pays off if rates are going up, right? So we would be indifferent between doing this or borrowing at 2% for 2 years. And we can apply the same interpretation here, right? Deposit at 1% for 1 year and simultaneously short an FRA at 3.01 and short an FRA at 5.03. Notice what we're doing now is we're doing 2 separate contracts to lock in one rate to make sure that we get a fixed rate of here it is right here, the 3%, the spot rate, to make sure we get that 3-year fixed rate, the spot rate itself. We have to involve 2 other contracts. If we're borrowing, we can borrow at 1% for 1 year and simultaneously go long the 1 year FRA 1 period out and go long the 1 year FRA 2 periods out at 5.03. Do you see the problem with all of this? Multiple contracts with multiple rates. If we're going to do this and have a series of cash flows here, and cash flows here, Isn't there one contract we can enter into that has a constant rate for multiple periods of time instead of having multiple contracts with multiple rates over multiple periods of time? Well, that is a swap. A swap takes all of these FRAs and says, there's got to be an easier way. That's what we're doing. Okay, I am going to lead you through the calculation or the determination of the fixed rate on a swap, the one single fixed rate we will use on a swap. And I will do it in a rather painless way, with less pain than what the module is demonstrating. But I do have to demonstrate an important concept of what a swap is kind of like. On the previous screen, we had calculated our implied forward rates as 1%, 3.01, and 5.03. The 1% really is the one-period spot rate, and we can refer to that as the implied forward rate at time 0 for one period. So we'll just assume these are all implied forward rates, and we can observe at this point in time what the first rate is, and we can calculate these two at this point in time. We have learned in previous modules that when we develop a derivative, we do it in such a way that there is a no arbitrage price. And that means that the value of the derivative for any time period, the value at inception is equal to 0. So we must set up a swap such that the value is 0. Consider a swap that is, let's say, receive fixed, pay floating, because we're swapping interest rate payments, right? Well, received fixed. If we were long a fixed rate bond, we would be receiving fixed. And if we were short a floating rate bond, since we're short, we would have to pay the coupon. We would be paying floating. So a receive fixed, pay floating bond is equivalent to being long a fixed rate bond and short a floating rate bond. So if we're long one bond and short another bond, if the sum of these two equals 0, the value of the swap must equal 0. So how do we get the value of the swap to equal 0? We find a rate, a fixed rate, such that a long fixed bond with that rate would be equal to the price of a short floating rate bond. We're helped out by the fact that a short floating, or I shouldn't say short, but a floating rate bond at inception is a par bond. Let me show you why. Imagine a $1 floating rate bond. Each coupon will be the floating rate. So on this example here, at this point in time, we know that the first coupon is going to be 1%. And we could use a series of FRAs to lock in 3.01 and 5.03. But at this point in time, we'll just assume that these will be, the implied floating rates will be the implied forward rates will be the floating rates. And then we will discount each coupon at the respective spot price. And our spot prices are in our denominator here. So our first coupon, it's a $1 bond. Our first coupon is a penny because it's 1%. Next coupon is 3.01 cents. The last coupon is 5.03 cents plus the future value. Discount it all back, and you will find that all of this equals $1. We have a par bond. So we never have to worry about the floating rate leg of a swap. It will always equal par. So our job just got easy. All we have to do is find a single fixed rate given the term structure of spot rates that creates a par bond. So for a $1 fixed rate bond, a par bond would be right here. We have a constant payment each time, and there's our future value, discounted at each of the respective spot rates. Well, we can write this in a slightly different way. Look at this term over here. All I've done was I've taken the numerator and I brought it to the side and I just put a 1 on top. Payment multiplied by 1 over Z1. We can see it's the same thing as this term. Do the same thing for each of them. And we're going to split this term up, payment and future value, into two terms, a payment term and a future value term. Remember, future value just equals 1. So I want you to see that this in blue is exactly the same thing that we have here. It's just expanded out, right? Well, 1 over Z1 we learned that's a discount factor. 1 over Z1 plus Z2 squared, that's the second discount factor. This is just a discount factor. So this is DF1, DF2, DF3, and of course that is DF3 as well. Well, look what we have. We have a constant term, payments, and then we have DF1 plus DF2 plus DF3. So let's do that. It's payment plus the sum of the discount factors. Since this equals 1, we could just take that out and say all we have at the end is discount factor 3, and there's plus discount factor 3. We're trying to figure out this term here. So let's take DF3 to the other side. We'll have 1 minus DF3 equals payment times the sum of the discount factors. Divide through by the sum of the discount factors. The fixed payment is 1 minus the last discount factor over the sum of all the discount factors. Now, when you see this formula, and you'll see it in level 2. You don't really see it here, but you will see it in level 2. It is the quickest, most direct way to calculate the fixed rate in a swap. The module shows you how to do it, first calculating the implied forward rates and then using the implied forward rates to determine what the fixed rate is. You don't have to. If we have all of the spot rates, that's all we need. We don't have to calculate any implied forward. We don't have to do anything. We just have to calculate the discount factors and calculate the fixed rate. Nice and simple. What the module was trying to do was to show you how the swap is equivalent to a series of forward rate agreements. And the forward rate agreements will use the forward rates. So it was showing you that, look, you can use those forward rates to calculate a fixed rate. Hence, the swap's fixed rate must be equivalent to those series of forward rates. So if you're just willing to take my word for it that they're equivalent, we can just skip all of the calculations and calculate a fixed rate directly, because we know that if we're looking at the floating rate leg, it is going to be a par bond automatically. The only job we have is to make the fixed rate $1 bond a par bond as well. And when we use $1 because when we solve for the payment, it will be in the form that we need, which is a decimal. That's why we use $1. As soon as we solve for PMT, because we will have the structure of the spot rates, we got our fixed rate on a swap. So on this screen, I'm going to prove it to you that this works. This is 1 minus DFN over the sum of all the discount factors. I'm going to prove it to you mathematically that it works, so that from here on you could just say, okay, I get it. A swap with a single rate is equivalent to a series of forward rate agreements, all with different rates using the implied forward rates. I get it. Thank you. Good enough. Let's move on. All right. Remember, we calculated these implied forward rates, and these were the spot rates that we observed at that time. So let's calculate the discount factors. This is 1 divided by 1.01. There's discount factor 1. 1 divided by 1.02 squared. When we calculate a discount factor, we're assuming a single unit payment 2 years from now because it's a spot rate. It's a 2-year spot rate. So we get 0.9611. And the last discount factor, 1 divided by 1.03 cubed, is 0.91. Add them up, you get 2.8664. That wasn't hard to do, right? Whatever series of spot rates we have, we turn them into discount factors, we add them up. Now we get the fixed rate by doing this. 1 minus the last discount factor divided by the sum of all the discount factors, 2.9604. And I know, when you look at this over here, you're saying, but how is that possible? Go back to the previous screen and follow step by step, and you'll see that it's just the present value of a bond. That's all it is, 2.9604. Not enough. I want to prove it to you that 2.9604 is in fact the fixed rate. So let's just use the floating rate as our FRA rate. And our first payment, 10,000, because it's 1%. We're going to assume $1 million. And here we're just going to say, well, let's say that we had a receive floating, pay fixed swap. So we want to receive the floating rate. The next interest payment that we had here is 3.01. Remember, when we use an FRA, we are locking in this rate, because if the rates in the market change, we'd get a different rate in the market, but any gain or loss would be offset by any gain or loss on the FRA, thereby locking in the rate. So here are the two interest payments. Now, if you're saying, well, this is 3.01, this is 5.03, I'm trying to keep as many decimal places as I can, because the rounding off errors, I want to try to minimize as much as the rounding off errors as I can. So this is what we would be receiving. On the first coupon date, we'd receive 10,000 because it's 1% of a million. On the second coupon date, we'd receive 30,000 because of the interest rate is 3.01 on a million. And on the third date, the last date, we'd receive 50,295. I'm saying that this is the fixed rate, 2.9604. So on a million, that means we're going to pay 29,000 here, 29,000 here, 29,000 here. Notice that we're paying the same amount each time. Well, let's take the present value of all the floating rate payments, and let's take the present value of all the fixed rate payments, and they should be equal such that the value at time 0 of the swap equals 0. So 10,000 will discount at 1.01, 30,099 discount at 1.02 squared, and the last one discount at 1.03 cubed. Here's the series of, here the present value of each of those cash flows. There's the total. Do the same thing down here. Discount each of these by their spot rates. Here's the total. 84,85826, 84,85718. We're off by about $1, a rounding discrepancy, because we're rounding off and we're working with a million, so we rounded off the interest rates, we rounded off this, we're rounding off the dollar amounts. You will find that if you don't round anything off, if you did this in a spreadsheet where it preserved all the decimal places, these two numbers would be identical. There is proof that this methodology right here will get you the fixed rate on a swap all the time, such that the present value of the floating rate leg equals the present value of the fixed rate leg. Now, let's talk about a swap. All right, let's define a swap. It is an agreement to exchange a series of cash flows, whereas a forward contract involves a single exchange. The FRA, which we've already been introduced to, is a single payment at the beginning of an interest rate period. Let's draw out a timeline. And we're at this point in time, we enter into a forward rate agreement. Well, it is for this period of time. That's why we need a forward rate. And as of this date over here, we know what the payoff is going to be, but the payoff is at the end of the period. But since we already know what it's going to be, we discount it back and we settle up over here. A swap, on the other hand, multiple payments that occur at the end of each interest rate period. So in a swap, let's do the same thing again. At this point in time, we observe what IFR 01 is, and we know what RFX, the fixed rate, is, and interest accrues over this period of time, and we settle up here. At this point in time, we will know what IFR 01 is, because if we're here, at this, just to back up a bit, at this point in time, the rate over here would be IFR 11. But once we're here, this rate now becomes the new IFR 01, and this rate stays constant. We let interest accrue. We settle up over here. So we settle up at the end of the period. Multiple payments that occur at the end of each interest rate period. And the value of the swap, much like every derivative, other than options, I should qualify that, other than options, all commitments, all derivatives that are commitments, will have a value of 0 at inception. And that is saying that the present value of the floating rate payments to be received or to be paid is equal to the present value of the fixed rate payments to be paid or received. Notice that these are opposite, right? Because if we're receiving these, we must be paying these. If we're paying these, we must be receiving these. Be careful in the reading. They leave out these words. And they just say floating rate payments received versus floating rate payments made. And you think, well, that's the payments I have received and I have made. When you leave out these words, you are implying that something is in the past when actually it's in the future. These words have to be in here. The floating rate payments to be received equal the present value of the fixed rate payments to be paid. At initiation, no initial cash flows are exchanged, but swaps do have counterparty risk because at each payment date, either I owe you or you owe me. So the payments are netted out. We'll see that shortly. There's no point in me sending you money and you sending me money. We figure out, well, who owes most, and then we just net it out, and one person pays. You have counterparty risk. 3-period swap will have one fixed rate. 3 FRAs will have 3 different rates. There's the big difference between them. A single 3-period swap is the same as 3 separate FRA contracts. We've already shown that in the first couple of screens, that if we used multiple FRAs, as opposed to just one swap, we come to the same conclusion. Rather than having 3 separate FRAs, we can come up with a single rate for a 3-period swap that would make us indifferent between using the swap versus using 3 separate FRA contracts, if it was a 3-period swap. Okay, so when we talk about the price of an interest rate swap, what we're really talking about is the fixed rate on an interest rate swap, and the fixed rate is called a par swap rate. I use R sub FX to denote the fixed rate on a swap. This reading uses S for swap, and N sub N to denote the number of periods the swap is for. The more common notation is R sub FX. S sub N is new notation that CFAI is introduced, and you may get confused because you won't see it anywhere else other than here. So I may as well introduce you to notation that you're more commonly going to see for a swap. So RFX is called a par swap rate. It is a multi-period break-even rate. An investor would be indifferent to paying the par swap rate or paying a series of forward rates that are all different. It is the single rate at which it is equivalent to a series of multi-period rates. So we'd be indifferent to that or to receiving it versus receiving the forward rates. Let's work on the valuation part of this now, because the value of the swap will change. For some of you who are paying close attention, you might have said, well, wait a minute here. If the fixed rate is, earlier we showed an example where the fixed rate was 2.96, and we showed the first interest rate payment where we would be receiving $10,000, but we got to pay out $29,000. We're out 18 grand. How is that going to work? So let's just look at this diagram that I took from the reading. It's a nice representation of the forward rates versus the spot rates. So we've figured out what our fixed rate would be. Don't worry about what these numbers here are. The important part is, notice this, for a 3-period swap, we have the same fixed rate each time. That is called the par swap rate. Notice that they use the notation S sub 3, S for swap, 3 for 3-period. And we have a series of implied forward rates. This one over here, notice that it is just simply Z1, but it can also be called IFR 01. Here is IFR 11 and IFR 21. Notice the difference. This rate is higher than this rate, but now this rate is higher than the fixed rate, and this rate is much higher than the fixed rate. So let's just use the numbers that I've been using so far, and we'll continue our example. And let's do a received fixed pay floating swap as we have already set up. And let's move to T1. Let's get our floating rate. Remember, it was 1%. We get $10,000 in. The present value of the remaining payments comes to $74,957. So once we receive the first payment, we have 2 more floating rate payments. The present value of those 2 add up to almost $75,000. So we receive 10, but we got to pay out 29 on the other side. So we pay 29.6 on the other side, and the present value of all the fixed rate payments left to be made is $55,564. So the value of the swap at this time is the present value of the floating rate leg minus the present value of the fixed rate leg is $19,410. You'll note that we paid roughly 19,600. We paid out 19,600 because we got 10 but paid out 29, so we're out 19,600, but the value of our swap is almost equal to what we paid out because the present value of the floating rate legs left to be received is now greater than the present value of the fixed rate leg to be paid. Let's fast forward to t equals 2. All we're doing here is we're just assuming that time is passing by. We're not assuming that the interest rates are changing at all, just that time is passing by, and that at each period of time, the floating rate that we see is equal to the implied forward rate. We're just doing the passage of time to isolate the effect of that. Here, we're going to receive $30,099, and we're still going to pay out $29,604. The present value of the floating rate payments left is $46,000. The present value of the fixed rate payments left is $27,000. If you subtract the two, you'll get $18,900. Notice that we have received roughly $40,100, and notice that we paid $59,200. So we're off by about $18,900. We have paid out about $18,900 more than we received. Look at the value of the swap. If we close the swap out that day, the other side would owe us that money. There we go. We've broken even. At any time, we've always broken even, because as we have a difference in cash, that will be reflected in the difference in the present value of the payments that are left. And if we're paying out more cash than we're receiving, the value of our swap should increase. If we're receiving more cash than we're paying, the value of our swap should be negative, so that we always have a zero value if interest rates don't change, just as time passes. Let's go all the way to the end. We get our last payment, $50,295. We make our last fixed payment. The present value of any floating payments left is 0. Present value of any fixed payments left is 0. And I've already shown you that if you took the present value of these three payments, it would equal the present value of these three payments. So earlier I said that on an interest rate payment date, one side doesn't pay the other and the other side pays the other counterparty. It's whoever owes, it will net out. Let's do that now. So notice here, this is our series of floating payments we would receive. This is the series of fixed payments we would make. Let's go to the first period. We're going to get $10,000, but we owe $29,000. So this side is going to send us $10,000, and we are going to send this side $29,000. Well, that seems like a waste of time. Why send me 10 if I'm going to send you 29? You keep the 10, and I'll just subtract it from the 29. So periodic settlement, we have three periodic settlements, is just MRR minus the fixed rate. And I make the note here that CFAI likes to use S sub n. So it's whatever the floating rate is minus the fixed rate times the notional amount times the period. We've set it up so that it's annual, so it's 365 over 365. It could be quarterly, it could be semi-annual. But if we multiply this out, 0.01 minus 0.029604, because that's the fixed rate on the very first payment date, that is the floating rate, times a million, we'll get negative 19,604, which makes sense, right? All we're doing is taking the 10,000 off the 29,000 and sending the other side 19,000 instead of them sending us 10 and then us sending them the 29. Let's just net it out. The present value of the floating rate payments left to be received, less the present value of the fixed rate payments left to be made, is 19,400. We are out 19,604. The value of the swap is 19,400. Notice it's very close to 0. These are not exact because of all of the different roundings that I've rounded off along the way. If you do this in a spreadsheet, you'll find that they're exact. Note, MRR01, this rate over here, is known at contract initiation date, but not all the other ones. We won't know what the floating rate is. We'll know what the implied forward rate is, but we won't actually know if the real interest rate will be equal to the implied forward rate until we get to this point in time. At this point in time, this becomes the new MRR01, and we will know it for sure. This will become the new MRR11. We won't know it yet. So, MRR11 will only be known at t equals 1 when it will be the new MRR01. And new spot rates will also be known, so a new MRR11 can be calculated because we do expect interest rates to change over time. They don't just stay static, they will change over time. So when we get to this period of time over here, there is no guarantee that that the rates that were attached to those two periods of time will still be the same rates. They may be different. So we have an important conclusion. This is how we calculate the value of the swap. The present value of the floating rate payments to be received or paid minus the present value of the fixed rate payments to be paid or received will change as time passes. And we've shown you on the previous screen how they change as time passes, but also change as rates change. And to demonstrate everything we've done so far, let's walk through example 3 and example 4, and we'll see how these two things affect the value of a swap. Example 3. Esther entered into a 3.5-year, $250 million interest rate swap contract under which it pays a fixed quarterly swap rate of 2.05% and receives 3-month MRR. So we're in a pay fixed, receive floating swap, 3.5 years, quarterly payments, which means there are 14 separate payments. The fixed swap price of 2.05% paid by Esther remains constant over the life of the contract. That is the definition of a swap rate. It is one fixed rate for the life of the contract. While the first 3-month MRR is known at t equals 0, and the first floating rate is really just the 1 period spot rate. It's the spot rate we would expect to see for a 3-month cash flow. The remaining 13 MRR settings are unknown, but are expected to equal the respective implied forward rates for each period through maturity. A prior lesson showed how IFRs are derived from zero rates, which were then used to solve for the fixed swap rate by setting the present value of the fixed payments equal to the present value of the floating payments. And we did this, except I showed you how to do it with nothing but the spot rates. You can use the implied forward rates if you want. It's the long way around. I showed you how to do it with the spot rates. The value of the swap contract will change as time passes. I've already shown you that. And as interest rates change. We first consider the passage of time with no change to expected interest rates. So we're going to isolate the two moves. I already gave you an example in the video where we just moved the time forward. We made the payment. We showed how well one side paid the other side too much, but that they made it up in the value of the swap changing. So we first consider the passage of time, no change to expected interest rates. That is, the MRR sets each period based on the implied forward rates at trade inception. So to assume just the passage of time, we must assume that at each period, the implied forward rate is the actual floating rate at that period. Assume the following implied forward rates apply to Esther swap at t equals 0. We need 14 of them. There's the 14. The very first one is just the same as the first period spot rate. So there are all our rates. Based on these forward rates, Esther expects to make a net swap payment each quarter through the 7th period. What are they saying here? Well, look at the 7th period. This is the floating rate payment, right? We're a pay fixed, receive floating. What are we paying? We're paying 2.05. So on the first period, we pay 2.05. We get 0.5 back. We're going to make a net payment. We make a net payment all the way to the 7th period. In the 8th period, the floating rate is now higher than the fixed rate, so we would be receiving payments for each payment after that. So we'll be making a net payment up to the 7th period, and then the last 7 periods we will be receiving a payment. So Esther expects to make a net swap payment each quarter through the 7th period, since the floating rate minus this is the fixed swap rate, 1.94 minus 2.05 is less than 0. For all of them, it's less than 0. And receive a net quarterly swap payment starting in the 8th period, where the floating rate minus the swap rate is greater than 0 for the final 7. Using equation 1, consider the periodic settlement values for the first 2 periods from Esther's perspective as the fixed rate payer. So here's the difference in rates. There's the floating rate minus the fixed rate. We see that's going to be negative, multiplied by the notional amount of $250 million, and the period is 1/4 of a year, is a 3-month period. So you can put 0.25 here, 3/12, however you want to write it. We should get a negative number, and we do. We know we get a negative number because the floating rate minus the fixed rate, the term in brackets here, is going to be less than 0. The notional amount is always positive and time is always positive, so it's this term that determines whether or not we receive, whether the net payment is something we make or something we receive. Negative. We should see the same thing for the second period, right? There's your floating rate, 0.74. There's your fixed rate, 2.05. That's going to be negative 818,750. What is the swap mark-to-market value from Esther's perspective immediately after the second periodic settlement if forward rates remain unchanged? Well, we know how to get to that. It would be the present value of all the floating rate payments yet to be received compared to the present value of all the fixed rate payments yet to be made. And we will take the present value of those floating payments, subtract the present value of those fixed payments, and it should equal, if you sum these two up, we should be very, very, very close to these two. Controlling for rounding errors, of course. Note that the swap price, the fixed rate of 2.05, was set at inception to equate the present value of the fixed versus the floating payments. Let's just skip this for now. This is just showing you the swap rate, and it's showing you the forward curve. And at period 1, we paid this rate up here. We received this. Same with period 2, 3, 4. It's not until period 8 where what we receive is above what we pay. Well, the first one is gone and the second one is gone. So it's asking us, what is the value immediately after these two are gone? As we move forward in time with no changes to interest rate expectations, the present value of the remaining floating payments, right? The present value of the remaining floating payments rises above the present value of the fixed payments at 2.05 as Esther has made a net settlement payment in the first 2 periods. What's going on here? What are they doing here? Well, what they're showing you is, let's put the y-axis now at period 2 because we're not at period 0. Period 1 is gone, period 2 is gone, so here we are. So now the first period goes out to here. So we would change all these numbers down here to say there's period 1, period 2, period 3. This part of the forward curve is gone. This is the original swap rate. This stays. So now you have to imagine, well, what would be the fixed rate? We know what the fixed rate is if we went from this part of the curve all the way up here, and we get this fixed rate. But what if we drop off the first 2 payments and we just consider all these higher implied forward rates? Well, we would have a higher new fixed swap rate. Since we're paying the fixed, what would we rather do? Would we rather pay this lower fixed or this higher fixed? Clearly, would rather pay the lower fixed. Anybody entering into this identical swap with now only 12 periods left would be facing this new higher swap rate. So compared to our swap, which has 12 periods left, and a new swap with 12 periods with the higher rate, clearly, visually, we have value because we get to pay a lower fixed rate. As the diagram shows, as time progresses, Esther realizes a mark-to-market gain on the swap since, and this is where it gets confusing, until you stick in the words to be. The present value of the floating payments to be received is greater than the sum of the present value of the fixed payments to be paid. If you just read it this way, it says the sum of the present value of the floating payments received. And well, 2 periods have gone by, so we think received is past tense. What does what we received have to do with anything? It is to be received on each one. And I'm sure if you went through this example and you were confused, suddenly those 2 words you say, okay, there we go, that makes sense. Note that this result depends on the relative level of the implied forward rates and the shape of the forward curve, which in this case is upward sloping. And if it were flat, then we would find that the fixed rate would equal every single implied forward rate. If it were downward sloping, it would be the opposite way around. So this conclusion is just because we have an upward sloping curve. If we instead consider interest rate changes only, okay, so interest rate changes only. All we did in this first example to get to this conclusion over here is all we did was cycle ahead 2 periods and say, let's assume that this curve did not change at all, that by the time we get to here and we calculate the forward rates, it would basically map onto this forward curve here. So now we're saying, let's do it the other way. Let's just consider interest changes only. In other words, no time will pass. We will enter a swap and instantaneously change rates so that we control for this time variable. Okay, if we consider interest rate changes only from Esther's perspective as the fixed rate payer and the floating rate receiver, we can show the conditions under which Esther has a swap mark-to-market gain or loss. Esther realizes a mark-to-market gain on the swap as the fixed rate payer if, again, stick in the 2B, the present value, the sum of the present value of the floating payments to be received would be greater than the fixed payments to be made, the present value, that is. And we would realize a mark-to-market loss if it were the other way around. A rise in the expected forward rates, keep this in mind now, we're paying fixed, receiving floating. A rise in the expected forward rates after inception will increase the present value of the floating payments. Let's stop there, because I want to make sure that you see it in your head. The fixed rate is fixed. It's fixed. It cannot possibly do anything to affect the value of the swap because it's fixed. It's only a change in interest rates. It can't be a change in the fixed rate. It must be a change in interest rates. If we're receiving the floating rate and rates go higher, we will receive a higher floating rate, but the fixed rate doesn't change. So if we're receiving a higher floating rate, we will be in this condition up here where the sum of the present value of the floating payments to be received would then be greater than the sum of the present value of the fixed payments to be paid, because this won't change, but this will be higher, right? That is, if we have received fixed, pay floating swap and rates rise, yay, throw a party. We show the effect of immediate change in interest rates following trade inception in the following diagram. So here's the original swap rate. Here is the original forward curve. Let's shift the forward curve up. We have a rise in rates. Now, if we use this new forward curve to calculate a new swap rate, it would be way up here. So we have entered into a swap with this red line here. That is our original swap rate. The forward curve immediately shifted up and another person came along and they now have to enter a swap at this higher rate. And they look at ours and they say, oh, you're lucky. You got this lower rate. And they got this higher rate. So if we're lucky and we got this lower rate, it must be worth something to us, right? The new forward curve in this diagram is composed of higher implied forward rates. If we were to now solve for a fixed swap rate using these higher IFRs by setting floating and fixed cash flows equal to one another, the new swap rate would be above the original swap rate. However, since Esther has locked in future fixed payments at the lower original swap rate while receiving higher expected future MRRs, the swap has positive mark-to-market value to Esther. So in going through this example, if you were frustrated, it's because this is missing in here 2 little words, to be received. The payments to be paid. In other words, the future. Because it makes no sense, because this is saying floating rate payments received sounds like past tense. But how do you get the present value of something that has happened in the past? You get the present value of anything that's going to happen in the future, so we can see that, well, it's a bit sloppy. You should have put in to be paid. Or you should have just put in future fixed payments and future floating payments. So if this one had you in grief because of those missing words and you're looking at it going, this makes no sense. This has to be wrong. It's backwards. No, it's just missing the words to be. Okay, Peloton. I think it's a play on Peloton. Peloton Investments entered into a 5-year received fixed $200 million pound interest rate swap in an example from an earlier lesson to increase the duration of its fixed income portfolio. Assume in this case that Peloton receives a fixed swap rate of 2.38% on a semi-annual basis versus 6-month MRR. Further assume that the initial 6-month MRR sets at 0.71% and, as in the case of Esther, the MRR curve is upward sloping. How will the value of Peloton's swap change as time passes and interest rates change? Let's stop right there and I'll highlight this so we can see exactly where we left off. We are going to be receiving 2.38% on a semi-annual basis, so our first payment that we would receive is 1.19% of the 200 million. And we'll be paying half the 0.71%, and since all rates are quoted annually, that 0.71 we divided by 2, we'll get 0.355 of the 200 million. The important thing is we'll be receiving more money than we'll be paying out. So at that point in time, since we received more than we paid out, the present value of everything we have left to pay out must be greater than the present value of all the money we still have to receive, because on day one they were equal. On day one they were equal, and after the first payment we received more than we paid, which means the present value of what we have to pay would be greater. We would have a mark-to-market loss. And that's an easy way to keep it straight. If on the first payment we ended up making a net payment, we must have a mark-to-market gain. If on the first payment we have net proceeds that we received, we must have a mark-to-market loss because they should offset each other. What about as rates change? And all we have to do here is think about what we're doing. We're receiving the fixed rate, or you could think about it in terms of we're paying the floating rate. What would you rather do? Pay a lower floating rate or a higher floating rate? Clearly a lower floating rate would be great. So if rates dropped, we would show another gain. We'd have the gain from the net payment we received, offset by a mark-to-market loss that offsets the difference, offset again by a mark-to-market gain for the change in rates. Depending on the magnitude of the change in rates, it might turn our mark-to-market loss based on the difference of what we paid into a gain, or it just might make the mark-to-market loss smaller. Either way, we're going to have a gain if rates drop, but we will have a loss if rates rise. First, consider the passage of time with no rate changes. The first period swap settlement, from Peloton's perspective as the fixed rate receiver, is 1,670. How do we get that? They're going to get 2.38. They're going to pay 0.71. If you ever wonder, how do you know whether the fixed or the floating is first or second? Put a negative sign in front of the pay, and that's where it goes. So receive fixed, pay floating, since negative is in front of pay, because when we pay, we part with money. That's a negative. Then we always know that here the negative sign is in the middle. We just got to figure out which rates go on each side. If we're receiving, we put it here. If we're paying, we put it there. Since it's receive fixed, pay floating, we put the 2.38 there. We put the floating rate over here, multiplied by the 200 million. And remember, I said it was for 6 months, so we have to multiply it by 0.5, which would be the same as dividing each of these rates by half, dividing them by 2, finding the difference, and then just multiplying by the 200 million. We get 1,670,000, which we would receive. That's a net payment we would receive. Well, if we received, the swap must have negative value for us. What is the mark-to-market value from Peloton's perspective immediately following the first settlement if implied forward rates remain the same as at trade inception? Because we said, let's just consider the passage of time. As the fixed rate receiver, Peloton will realize a mark-to-market loss on the swap, since the sum of the present value of the floating payments to be paid will now be greater than the sum of the present value of the fixed payments to be received. So an easy way to keep it straight is if we received a net payment, we must have a mark-to-market loss from the passage of time. If we made a net payment, we must have a mark-to-market gain because of the passage of time. All right, second, consider a change in the forward rates. And to do this, we're going to say, let's not have time pass. Let's just change rates so that we can visually separate the two and see the difference. A decline in expected forward rates immediately following trade inception, so no time has passed. A decline will reduce the present value of the floating payments, right? We have lower rates and we have to pay those floating rate payments. Well, if we have to pay less than what we originally agreed to, it must reduce the present value of all those future payments. The fixed swap rate will remain the same. Peloton will realize a mark-to-market gain as the fixed rate receiver, since the sum of the present value of the fixed rate payments to be received will now be greater than the sum of the present value of the floating rate payments to be paid. This mark-to-market gain is shown by the different size of the shaded areas under the original swap rate using the new forward curve in the following diagram. So what we're showing here is this red line here was the original swap rate, and this green line was the original forward curve, such that the area under the curve under here would have been equal to the area made up by this triangle over here. These two areas would have been the same. But we said rates dropped, so push the forward curve over to here to this light blue dotted line, and if we then calculated what the fixed rate would be based on this curve, this is what the new swap rate would be. However, we have the old swap rate. So now the payments are this area, this triangle here, versus this triangle here. You can see that the area under the curve here is greater than the area under the curve here. It's just a visual way to show you that, hey, this is worth more than this now. The present value of the fixed leg is now worth more than the present value of the floating leg, because we get to receive the higher fixed rate, not this lower one. However, we get to pay the new lower forward rate. There we go.